In this course, we are going to build the basic elements of a game that is similar to the old Atari classic Marble Madness that was created by Mark Cerny. We will design a player that controls a marble that can roll over the ground using basic physics. It will also have a dash ability and an ability to roll across a wall to avoid falling into a pit. Finally, we will introduce a checkpoint object that can work as the start and end position for each level. The player will be able to roll the marble into the checkpoint where it will be captured. After the marble is held in place, we will present the player with an option to teleport back to the starting checkpoint. We will start by creating a clone of the starter project. You can either build this starter project by following the player controller video that is linked under this video, or you can simply download the project from the repo that is also linked. I will often begin work on a project by changing some engine features to improve performance simply to make development a smoother process. We will start by opening up the editor preferences and setting the Asset Editor Open location to Main Window. This ensures that all of the assets we open appear as tabs in the same window instead of opening up as separate windows. We can now open up the project settings to change a few rendering options. I will turn off lumen lighting effects by setting the dynamic global illumination setting to none and setting the reflection method to none. Finally, I will turn off nanite rendering. This will require a restart of the editor. After the restart, we can also delete the floor object that is in the level. We are going to create a new platform object that we can use to build out the entire test level. Let's get started building the actual game by looking at the input actions we have available from the starter project. Since we are creating a player that is a bit different from the normal third-person character, we will need to alter some things about how we design the player blueprint. We do not need the use input action for this project, so we can delete it. It will warn you that it is currently being used, but you can force the deletion. Now let's create two new input actions that we will need for controlling the marble. Create one action called IA_start and another called IA_boost. After that, we can open up the input mapping context and create bindings for these new actions. Assign the IA start action to the Enter key, then assign the IA boost action to the E key. We will use the start action to respawn the player back at the start of the level, and we will use the boost action to give the marble a sudden increase in forward velocity to help the player clear larger gaps. You can now save the input mapping context and then close it. That is all of the input changes we will need for this project. Let's now deal with the broken character we caused by deleting the use action. If we look at the blueprint, we can see it has an error due to the missing asset. We can solve this by simply deleting the main character blueprint. Our marble is not going to be a character. We will model it as a pawn that is affected more directly by physics instead of using the character movement component. This main character blueprint was also referenced by our game mode. So if we take a look at the GM_main blueprint, we can see the player pawn field is now set to none. Let's create our marble blueprint to take its place. Go into the player folder and create a new blueprint called BP_marble. Select pawn as its parent class and then open the blueprint so we can begin working on it. We will first set up the components for the marble. Add a new scene component and call it root. Then replace the existing default scene root. Now add a sphere static mesh and call it mesh. We will next set up the player's camera. Add a spring arm component and keep its default name, then add a plain camera component and also keep its default name. That is all of the components we need for the marble. Let's now update some settings for these components. We want the marble's camera to be driven by the rotation of the player controller. So select BP Marble from the component list and then look for the pawn option called Use Controller Rotation Pitch. Right underneath that setting should be a similar one for the yaw. Set both of these to true by checking the box. Now we want to add a material to the marble, so let's start by creating a new material we can use. Return to the content drawer and create a new material called m_marble. You can change the appearance of this material to whatever you prefer for your game, but we do need to add a parameter to this material to allow us to create the teleportation effect we are going to use later. First, set the blend mode for this material to masked. This will allow us to set an opacity mask to hide some of the pixels being displayed by this material. Now, add a scalar parameter called Dither alpha. We will use a technique called dithering to create a simple fade-out effect for the marble without needing to write a more complicated shader. Dithering is an old technique that is used to blend colors using an optical illusion. The effect is caused by switching between the colors for each pixel in the region where we want them to appear blended. Our eyes will naturally blend the colors together if we view the pixels from far enough away. In our case, we are not going to use the technique to blend together two colors, but instead we will make some of the pixels transparent. This will cause it to look like the marble is fading away as more and more pixels disappear. We are creating this parameter to allow us to control what percentage of the marble's pixels are transparent. As we move the Dither alpha parameter from 1 down to 0, the marble will disappear completely. We can then reverse this to bring the marble back into view. We're now going to introduce a texture for the marble. You can use this same texture by downloading the completed project from the repo, or you can use your own texture. If you drag the image into the player folder, Unreal should generate the texture asset for you. Then you can drag that asset into the graph to automatically create a texture sample node. Hook up the RGB output from the texture sample to the base color for the material. Finally, to apply the dithering, we will use a built-in node called Dither Temporal AA. This node can take our Dither alpha scalar as its alpha threshold input. Make sure you also connect the output of the node to the opacity mask input on the material. And if you want to experiment with the differences between random and regular dithering, you can make changes to the second input called random once we have this up and running. Now, change the settings to get the appearance for the marble that you prefer. Remember, once you have the basic game up and running, you can also turn back on things like Lumen to get better visual output for the marble. Let's save and apply our changes to the material, then you can close it and return to the marble blueprint. To avoid needing to click compile and save every time, you can also select this option next to compile to have Unreal automatically save every time you successfully compile a blueprint. We will also need to create a physical material for the marble. Remember, we are not using the normal character movement component to control the player's movement. We want to apply a physics material to the marble so that we can control things like the friction and bounciness of the marble as it rolls around the level. In the player folder, create a new physical material. If you search for physics, you should be able to find physical material under the physics category. Once you click it, then choose the physical material option, name it PM_marble, and open it up in the editor. We will change the friction and the static friction to 5. This will make it so that the marble almost never slides around on the ground. This will make the player's experience a lot better when they are trying to roll up hills or land on a platform after a fast jump. Static friction affects how easy it is for the marble to start sliding when it is at rest, and the regular friction setting affects how much the marble slips when it has already begun sliding on the ground. We will also set the restitution to 0. This will make it so that the marble will not bounce when it lands on the ground. All of these settings can be changed to create the experience you prefer for the game, but I am basically starting with settings that will make the marble easier to control. Now, we can finally apply the two materials we have just set up. Select the regular marble material we created under the Materials section. Then scroll down to the Physics section. We will also set a few related values while we're here. Set Simulate Physics to True so that the marble reacts to the physical forces. Change the linear damping to 1 and the angular damping to 8. These settings are somewhat related to the friction settings. A higher linear damping value will cause the marble to slow down faster after the player lets go of the movement keys, and a higher angular damping value will cause the marble to slow down its rolling speed more quickly. Increasing both of these values will once again make it easier to control the marble without it rolling off the edge, but in some sense it will make the physics feel a little less realistic. Also make sure you set Enable Gravity to False here. We are going to apply our own gravity force using the blueprints. Now scroll down to the Collision category and set the physical material we created using the Override setting. Compile and save this blueprint. Now select the Camera Spring Arm component. We will rotate the Y value of the component to -30 degrees. And we will also increase the length of the arm to 800 centimeters. If you look at the viewport, you can see this will place the camera above the marble looking down at it with a slight angle from a third-person perspective. Let's now define all of the variables we are going to need to write the marble's blueprint. Create a float variable called ground torque. Torque is a word that refers to the force being applied to roll or spin an object. Create a second float variable called wall torque. We will have two different forces for moving the marble depending on whether it is rolling along the ground or rolling on a wall. When it is rolling on the wall, this will be similar to what would be called a wall run technique if we had a normal character. Next, create another float variable called wall force. The reason we want this variable is to define a small force that will alter the marble's movement when it begins a wall run. Now, define another float variable called jump impulse. This will be a sudden change in velocity we will use to allow the marble to jump upwards. Unlike a force, which would gradually push an object, an impulse will cause a sudden jolt. This is much more like the platformer jump most people are used to. We will also create a similar float variable called boost impulse. Set this variable to public. This variable will define the power of the player's boost ability. But we also want another related float called boost impulse max, because every time the player uses their boost ability, their boost impulse will go down to 0, and they will only be able to perform the boost again after it has increased back up to the maximum. So we need to keep track of the maximum separately because we will set boost impulse to 0 after every use, then track its progress back up to the maximum. Create another float variable called contact trace distance. We will talk more about this variable when we use it, but it basically controls how the marble checks to see if it is touching any walls. Now create a variable called material instance and set its value to a dynamic material instance object reference. This is where we will store a copy of the marble material so that we can change its parameters without changing the source material. Create a related float variable called material alpha. This will be the value we use to set how transparent the marble is when we are creating the dither effect during teleportation. Set this variable to be public. Finally, create one last variable called GameModeRef and set its type to a GMMain object reference. This is simply how the marble will communicate with the game mode blueprint, which will be managing a lot of the gameplay mechanics. That is all of the variables we are going to define. Now you can compile and save the blueprint so that we can set their default values. Click on BP Marble under the Components list and then in the Details window look for the Default section where you can set all of the default values for these variables. Now go through and assign all of the values you see on screen. There is no default for the material instance because we will create its value in the blueprint. Return to the content drawer and create a new folder called UI. We are now going to create the widget we will use to display the UI. In the new folder, create a new asset and search for widget. Select the widget blueprint and choose user widget as the parent class. Call it WBP_interface and open it in the editor. Start by adding a canvas panel from the palette on the upper left. This gives us a full screen widget to work with. Now select the canvas and add a progress bar as a child. Then add two text widgets as children next to it. Call the progress bar Boost Bar. Call the first text Boost Label and call the second text Restart Label. Grab the Restart label and pull it over towards the center of the screen to get it out of the way. Now select the progress bar and set its position X and position Y to 35. Set its size X to 250 and size Y to 45. Open up the background image under the Style category. Set its tint to a dark gray color. This will be the background color of the Boost Progress bar, which will show when the bar is empty. Next, create a new binding for the percent value. This will automatically jump you to the function graph. Return to the designer for the WBP interface. Select the fill color you want for the boost bar under Appearance. This will be the actual color you see when the progress bar is full. Now we can define the positioning of the boost label. Set its position X and position Y to 45. Set its size X to 151 and its size Y to 40. You can also add the string boost to the text field. In the search field for the details window, search for shadow. We're going to add a drop shadow effect to the text to make it stand out better. Set the offset to 3:3 and set the color to pure black. Now you can clear the search field and select the Restart Label widget. First, set the anchor to center. Set its position to 0, 0. Set its size X to 327 and size Y to 40. Then set its alignment to 0.5, 0.5 so that it is perfectly centered in the screen. And we can actually set size to content to true so that we don't have to worry about getting the X size correct. In the text field, type "Press Enter to restart." Under the font category, set the size to 48. Now we also want to apply a drop shadow to the restart label. First, select the restart label, then search for shadow again. Set the offset to 5.5 and set the color to pure black. Make sure the alpha is set to 1 for these colors so they are not transparent even if they look black. Finally, we want to search for the visibility setting, because we want this label to be hidden when we start the game. We are only going to show it once the player reaches the end and is ready to be teleported back to the start. Now compile and save the interface blueprint. One last thing we need to do is set the restart label to be a variable by setting isVariable to true. This is because we need to update its visibility from the blueprint later so it can be shown to the player. Let's now write the function we bound to the percent value for the boost progress bar. You can double-click on the function from the list on the left to jump to the function graph. First, we will call getOwningPlayerPawn to get access to the marble. We then have to cast the return value to BP marble because we need to access its fields to calculate the percentage. And those fields do not exist for the generic object that is returned by the function. On success, we will get the boost impulse and boost impulse max values from the marble and then divide them to find the current percentage. We can then return that value directly. That completes the function. You can compile and save the blueprint. We will now create a new function called setRestartTextVisible. We will call this function to show the restart label to the player after they have finished the ending sequence. Add a new input to this function called inIsVisible and give it the Boolean type. This input will tell us whether we are trying to hide the restart text or make it visible again. So let's start by branching on this input and creating two paths with reroute nodes. Both paths will look very similar. We can call the setVisibility function by getting a reference to the restart label from the variables list. This is why we needed to make the restart label a variable from the designer. For the true path, set the input invisibility to visible, and for the false path, set it to hidden. Compile and save the blueprint and close it. We are done editing the interface. The next thing we are going to do is create two enumerations to keep track of the overall state of the game. Create one called e_game_stage and create another called e_control_stage. Now open the game stage one in the editor. Add three variants to this enumeration. Call them play, respawn, and finished. We will go into more detail about each stage as we build the game mode logic. For now, just save this enumeration. Now open the control stage enumeration. Add 5 variants to this one and call them free, stasis, tractor, fade in, and fade out. When the marble is being controlled by the game instead of the player, these will keep track of what kind of control is happening. Save this enumeration and then close both of these new assets. Let's begin building everything we need to create the level. Go back to the content drawer and create a new folder called World. Inside this folder, create 3 new materials. Call them m_base, m_platform, and m_wall. We do not need to do anything special with these three materials, so make them look however you prefer. Base will be applied to the top and bottom of the checkpoints in the level, platform will be applied to all of the floors, and wall will be applied to the walls they can roll across. Now go back to the content drawer and create one more material. Call it m_beam. This material will be a little different than the others because we want to control it from the blueprints. Open it in the editor. First, set its blend mode to translucent so that we can see through the material like glass. Now add a vector parameter to the graph and call it beam color. Connect the RGB output into the base color for the material, then set the opacity to a small value like 0.05. You can set the default color of the parameter to anything you like because this will be changed in the blueprint. The only time you'll ever see the color you set here is when looking at the checkpoint asset in the content drawer. Make sure all four of these materials are saved and close all of them to clean up the editor. Now go back to the World folder in the content drawer and create a new blueprint. Select Actor as its parent class and call it BP_checkpoint. Open this blueprint in the editor. We'll start by setting up its components. Add a capsule component and then set it to be the root component. Then add a cylinder static mesh as its child and call it beam. Add two more cylinders and make sure they are all children of the capsule. Call them top cap and bottom cap. Now, add one scene component and call it spawn target. This will be the location we use when we want to teleport the player to this checkpoint. Leave it at its default location right in the center. Select the capsule and set its scale to 222, then set its mobility to static. Change its capsule height to 200 and its capsule radius to 100. We now want to arrange the static meshes so they line up nicely with this capsule component. Select the beam and also change its scale to 222. Set its mobility to static, and then assign the m_beam material to it. The capsule is going to drive the collision response for recognizing the player, so go down to the beam's collision category and set its preset to no collision. Now select the bottom cap mesh and change the Z value of its location to -150. This time, set its scale to 2 to 1, and then assign it the m_base material. Let's also turn off the shadow casting for the caps. Now we'll do almost the same thing for the top cap. Set its z value to 150 and set its scale to 2 to 1. Also assign it the m_base material, then set cast shadow to false. Let's now introduce a new variable called beam color and set its type to linear color. Make this variable public. Now open up the construction script. This is where we are going to create the dynamic material instance that will allow us to make changes to the checkpoint's material using the beam color parameter we set up earlier. Get a reference to the beam component and then call create dynamic material instance on it. Select the mBeam material as the source material. We can now take the return value and use it to call setVectorParameterValue on the new material instance. You can always go back to the parameter definition to help avoid any typing errors, because this parameter name has to match exactly with the definition for it to work. And the worst part is that if it doesn't match, you will not get any errors. It will just silently fail by doing nothing. This should actually be set vector parameter value, not set scalar parameter value. Paste in the parameter name and then use the beam color variable we just defined as the input for the value. This way we can use the beam color variable to select the color of the checkpoint's beam when we place it in the level, and each checkpoint can have its own color set. Compile and save the blueprint, and then go to the viewport to test this. You should be able to change the beam color value and see the color appear in the viewport. You can now close the checkpoint and the beam material. Let's open up the gm_main blueprint so we can start working on the game mode logic. This is where most of the work for running the level is going to exist. The first thing we want to do is replace that player pawn class we broke way back at the beginning of the video. If your blueprint did not open up as a data-only blueprint, then you can find these settings under the class defaults at the top middle of the screen. Select the BP Marble class we defined as the new player pawn. This will ensure that the game mode automatically spawns our marble into the world. Compile and save the blueprint, then click on the link to open the full blueprint editor. We'll start by adding a few variables to the class. Add a new variable called InterfaceRef. For its type, use a WBP interface object reference. Next, add an object reference for the BP Marble class. Call this MarbleRef. We now want to define two variables to hold references to the start and end checkpoints, but we will have to define the related classes first. Return to the content drawer and go into the World folder. In here, we can right-click on the checkpoint class and choose the option to create a child blueprint class. This will create a new blueprint class that inherits from the BP checkpoint. Call the first one BP_start, and then create a second child and call it BP_finish. Save both of these blueprints. Now open the Start blueprint in the editor. We can use the beam color variable that it inherits from the checkpoint class to define its color. Choose whatever color you want to use for the starting point of your level. If everything is set up correctly, you should be able to see the color change in the viewport as you change the color. After you've got the color set, compile and save this blueprint and then open the Finish blueprint. Here, you can set the color you want to use for the finish of your level. After that, compile and save the blueprint. We can now return to the Game Mode class and set up the two variables we will use to refer to the checkpoints. Make all of these reference variables public so we can access them from other scripts that interact with the game mode. Let's now create two variables to track the current state of the game. Create one variable called GameStage and give it the eGameStage enumeration as a type, and then create a second variable called ControlStage and give it the eControlStage as a type. We also want to set these two variables to be public. Now create a variable called ControlTarget and set its type to vector. This will be used as the target position when the game is teleporting the marble to a new location. Compile and save so we can check the default values for the variables. We want GameStage to be set to the value play and ControlStage to be set to the value free. These are likely the default values already, but just check them quickly to be sure. Now we can begin working on the event graph for this blueprint. Let's create two custom events that will respond to major events in the game. Call the first event Respawn and call the second event Finished. We can now locate all of the references we are going to need for our variables in the Begin Play event. We are going to use a function called getActorOfClass. Notice the actor is singular, which means it will always return at most one actor. In our case, each of these classes should only be placed into the level once. Begin by searching for the BP_start class, and then take the return value and use it to set the startRef variable. Now, follow the exact same process to set the FinishRef variable. Finally, use the same process to set the MarbleRef variable. Now let's begin working on the two custom events we defined. We are going to define a few helper functions to handle these events because there is some overlap between the work that they will be doing. Let's define a new function called ControlUpdate. This function is going to handle all of the different ways in which the game mode can take control of the player. For instance, when the marble rolls off the edge of a platform, the marble will fade away, then be teleported back to the start checkpoint, and fade back into view. This will all be handled by the control update function. So the first thing we want to do in this function is check to see what type of control is currently active. We can do this by using a switch statement on the control stage variable. This will give us a unique execution path for each variant of the control stage enumeration. We will use reroute nodes to create a path for 3 of these variants: tractor, fade in, and fade out. We will start by defining the tractor path. In this case, the marble is actively being pulled to a new location by the game, so we are going to need to make sure that the player can no longer control the movement of the marble. They shouldn't be able to use their boost ability or jump or anything like that. We will allow them to rotate the camera, but the position of the camera will follow the marble as it is controlled by the game mode. To do the movement, we are going to use a function called vinterp2. This is a function that interpolates between 2 vectors based on an input time and speed. The first thing we need to calculate is the starting and ending point for the movement. We will start at the current location of the marble. We can use the marble ref we set up earlier to get a reference to its mesh, and then call getWorldLocation to find its current location. Connect this directly to the current input. The target for our interpolation is simple because we have already defined a variable where we are going to store the current target for any controlled movement. It is called control target. We will use a constant delta time specifically because we are going to call the control update function from a timer. This means we will be able to set exactly how long it waits until calling control update each loop. We will use 0.01 seconds for the timer's update. Let's actually store this value in a new variable because we will use it multiple times. After setting the variable to 0.01, we can connect it to the delta time input. Finally, we can use 5 for the interpolation speed. This controls how quickly it will move between the 2 vectors. Now the return value of this node will give us the new location we can use to update the position of the marble. Use another reference to the marble's mesh in order to call setWorldLocation, and connect the location we just calculated to the new location input of this node. We also want to set teleport to true. This means the marble will essentially forget its previous physics state while it is being teleported. We can begin the next step by copying the 2 inputs we created for the interpolation in the previous step. We want to call distance squared on the 2 vectors to check how far apart they are. We don't actually care about the exact distance, so we are using the squared version to avoid calculating the square root for no reason. We can now check to see if the marble has almost arrived at its destination. If this distance squared is less than 1 centimeter squared, we will consider the teleportation to be finished and move on to the next stage. The next step depends on what game stage is currently active. This is because the teleportation stage can happen in multiple situations. If the marble falls into the pit, it will be teleported back to the start. But if the marble completes the level and chooses to restart, it will also be teleported back to the start. So we will use a switch on the game stage enumeration to now decide how to go forward at this point. If the marble is currently being respawned, then it has just traveled back to the start from the finish checkpoint. It is currently invisible because it will fade out before we teleport it back. This means we need to update the control stage to fade in. But if the marble is in the finished state, then it has just been dragged into the end checkpoint where it should be held in place while we wait to see if the player presses enter to restart the level. In this case, the marble should be in the stasis control stage. In this second case, we will also want to call the setRestartTextVisible function that we created on WBP interface, because the player should be prompted to know they can press enter to respawn back to the start as soon as their marble has been placed in stasis in the finish checkpoint. That completes this entire path. You can clean up the graph a little bit, and then we'll move on to writing the fade in path. For this path, we are going to use an interpolation, but it will not control the location of the marble. Instead, it will control visibility of the marble through the Dither effect that we talked about earlier in the video. Start by getting a reference to the marble's material alpha variable. We are now going to use the function finterp2 to gradually move between the current alpha value and the target. In this case, we are trying to fade in the marble, so our target should be 1 because 1 represents a fully visible marble. We can use the same control update delta variable we created earlier to set the delta time for this interpolation as well. This is because the control update function will always be called on this same interval by the timer we will set up shortly. We can also use a speed of 5 for this interpolation, but you can come back here later and experiment with these speeds if the fading or teleportation speeds do not seem right to you. Let's now use the output of this interpolation to set the new value of the marble's material alpha. We now want to do a similar check to see if the fade-in process should be completed. We can check to see if the material alpha value is less than 0.05 to see if the fade-in is almost complete. We will once again create two paths to handle each situation. For the true path, the marble is still in the middle of the fade in. In this case, we simply want to update the marble's material to the new alpha value so that it becomes a bit more visible than it was before. Feel free to once again go back to the marble's material and copy the parameter name to avoid any typos. In this case, the parameter is called Dither alpha. And the value we want to set is the newly updated material alpha value from the marble itself. This is all that needs to be done for this path. This condition here should actually be less than 0.95. This is the fade in path, so we want this branch to tell us whether the fade is still active. It will only be complete when the alpha gets close to 1, so we will check to see if it is still less than 0.95 to decide if it has not reached its goal yet. For the false path, we can copy all of the parameter update nodes we used above for the true path. The only difference is that we first want to snap the material alpha value up to 1. This ensures the marble actually ends its fade-in process at exactly 1, which is fully visible instead of just getting close. Let's first enable the collision for the marble's mesh. This is because after the marble has faded back in, it will always be about to enter gameplay again no matter what stage it is currently in. This means it will need to be able to collide with the platforms. When we start teleporting the marble, we will turn off its collision so that it doesn't get stuck on a platform when we are trying to do something like pull it out of a pit. After that, we will also set the spring arm for the camera to do a collision test for the exact same reason. Regular gameplay is about to begin again, so we don't want the camera passing through walls anymore. We can finally complete this path by updating the enumeration values so the marble enters into the next stage. In this case, we want the marble's control stage to be free and its game stage to be play. This means the game mode will have no control over its movement anymore. We can now clean up the graph a little bit to make sure we still have room for the final control stage we are going to handle next. As you can tell from the names, the fade-out path is going to be very similar to the fade-in path. Let's begin by copying the interpolation process we used for the fade-in. Paste all of these nodes at the beginning of the path, and then we only have to make one change. We now want to move from the current alpha down to 0. This will slowly fade out the visibility of the marble instead of fading it in. Then we want to do the same kind of completion check we've done with the other paths. But we want to make sure the condition is different. In this case, the fade out will still be active when the alpha value is greater than 0.05. For the true path, we can copy the exact nodes we used for the true path of the fade-in stage. For the false path, we can also copy the exact same nodes, but we will have to make one small change. Once the alpha value is almost equal to 0, we want to snap it to 0 so that the marble is fully invisible when we go to teleport it. The next step depends on what game stage is active. We are going to check if it is currently equal to respawn. If this is true, then the player pressed enter to restart the level, and the fade out of the marble has just finished. This means the marble is ready to be teleported back to the starting point. The first thing we will do is set the control target vector that we are using to define the target of the teleportation. We can get the actor location of the start checkpoint and use it to set the control target. After this, we want to set the control stage to be tractor so that the marble begins moving towards the new control target. And finally, we want to hide the restart text because we now know the player has just pressed enter to restart. Make sure this input is set to false by leaving the box unchecked. That completes all three paths of the control update function, which is the largest function in this entire build. Let's now work on the respawn event. This event will be fired when the player presses enter to restart the level. The first thing we want to do is turn off the collision on the marble's mesh. This is because we are about to take control of the marble and teleport it back to the start, so we don't want it colliding with the level while we move it. Sometimes it will need to pass through a wall to get back to the start in a straight line. The next thing we will do is turn off the marble's cast shadow feature, just because it can look strange when the marble is being moved around by the game mode. This part is not essential. The next thing we will do is update the stage variables. We will set the game stage to respawn and the control stage to fade out. We also want to set the control target to the location of the start actor so that it knows where to teleport the marble. And then we're finally going to start the timer that calls the control update function. This is what allows the game mode to take over the marble. We will use the node called setTimerByFunctionName. You can copy the name of the function from the functions list on the left, because this is another case where it has to match exactly or it will fail silently. We can then use the control update delta variable we defined earlier to set the update interval for the timer. This ensures the control update function will be called regularly every 0.01 seconds. And then we can set looping to true so that the function continually gets called over and over until we tell it to stop. That completes the respawn event. You can clean up the graph a bit and then we'll move on to the finished event. The finished event is going to be very similar to the respawn event. We can begin by copying the first section of the code from respawn. Connect this section to the entry for the finished event after you paste it, and then copy the two stage variable updates. We will need to change the values that are updated for the finished event. Set the game stage to finished and set the control stage to tractor. This is because when the player first enters the finished checkpoint, they will be pulled into it and then held in place at the spawn target component we created earlier. This also means we need to set the control target to be the finish ref's actor location, so that the control update function knows where to move the marble. Finally, we also want to start the timer for the control update function at the end of this event. We do not need to change any of its details because the specifics of the update are all controlled by the values we've set for the game stage and control stage variables. We now need to set up the finish checkpoint so that it responds to the player when they enter the beam. Open the BP Finish Checkpoint blueprint. Begin by adding the onComponentBegin overlap event to the capsule component. We now want to open the marble blueprint so that we can add a tag to it. In the marble blueprint, you can select the top component of the hierarchy and then search for tag in the details window. Here you can define an actor tag for the marble. Just call it marble. Now compile and save the blueprint and return to the finish blueprint again. The first thing we will do in this event response is check if the other actor that has overlapped with the capsule has this marble tag. If this is true, then we will call getGameMode to get a reference to the game mode and then cast it to our specific class so we can call its unique functions. Once we have a reference to our game mode, we can trigger the finish event by using the finished node on the GM main reference. Now compile and save the finished blueprint. We can close these blueprints and start setting up our level that we will use to test all of these features. To set up this level, we need to create one more simple blueprint that we will use to create the platforms and walls of the level. In the World folder, create a new blueprint called BP_platform and select Actor as its parent class. Add a cube static mesh and make it the root component. Now change the scale of the cube to 10, 10, 2 and assign the M platform material to the first slot. Compile and save this blueprint and then close it in the editor. We also want to open up the player controller blueprint so that we can create the interface widget when the level begins. Go to the event graph to the point after we add the mapping context and add a create widget node. Select the WBP interface as the class and get a reference to self to use as the owning player. After that, we can use the return value to call add to viewport so the widget is placed onto the screen. The last thing we need to do is set the interface ref variable for the game mode. It is the only one of the references we didn't set in begin play because it is created by the player controller. So it doesn't already exist in the level to be found by getActorOfClass. Call getGameMode and then cast it to our specific class, then use the reference to set the interface variable. You'll need to route the interface value along the bottom over to this set function. That's all we need to do for the level preparations. We're now going to create a series of platforms around the level and then place our start and finish checkpoints to create a test level. You can design the level in any way you want. There's no fundamental distinction between walls and platforms. They are all the same basic platform object. It will just be how the marble contacts them that determines when they will be treated as a wall. But we did create the wall material that you can apply to your walls, basically just to provide some visual distinction between the different elements of the level. You can rotate the platforms and change their materials as you place them in the level. The only thing you'll want to ensure is that the level is possible to complete. Basically, keep platforms about one platform length away from each other, otherwise it will be a bit difficult to make the jumps when you test your level. It is possible to make a much longer gap if you have a long extended wall next to it because you'll be able to use the wall run feature, and you should have at least one of these so that that feature can be tested. And finally, make sure you have one start checkpoint and one finish checkpoint in the level in places that can be reached. You don't necessarily have to start the marble at the start checkpoint. The start checkpoint will just be where the marble is respawned after it falls into the pit or completes the level. But you can place the player start object anywhere else to set the first place the marble will show up in the level. Now that we've got the test level fully set up, we are going to move on to the last major part of this build. We need to set up the marble blueprint so that it has all of its abilities like the boost and the wall run. Open up the BP Marble blueprint. We'll start with the begin play event. Get a reference to the mesh and then use it to call Create Dynamic Material Instance. Select mMarble as the source material. After this, we want to store a reference to the game mode in the variable we set up. After calling getGameMode, make sure you cast the return value to the GMMain class before trying to store it in the GameModeRef variable. Now we can move on to the tick event. The first thing we'll do every tick is sync the actor's location with the mesh's location. This is because we are going to use the physics of the mesh to control the player, so we'll need to update the actor so that it is always at the same position after the mesh moves due to forces. We can synchronize these two positions by simply setting the actor's location to be equal to the mesh's world location each tick. The reason we do not just make the mesh into the root component is because it is going to be constantly rotating as the player moves through the level. And this is a problem because the camera is attached to the root. This way our camera can remain stable while the marble rolls, but the entire actor will still update its position to match the marble. The next thing we will do is check to see if the game is currently in the play stage. If this is true, then we can apply the force of gravity to the marble. Get a reference to the mesh and then use it to call the addForce function. We can create a new vector and set its z value to -3000, then use this as the force input. But we only want to apply this force of gravity if the player's marble is not currently being controlled. That's why we check to see if the game stage was play first. The next thing we will do is check to see if the marble has fallen off the platforms. We can call getActorLocation and then check to see if the z value is less than -50. If this is true, then we trigger the respawn event. First, we can turn off the spring arms collision check because we are about to teleport the marble back to the start. Then we can use the game mode reference variable to call respawn. That completes the tick event. You can now take a moment to clean up this graph. Let's now create a new function that will tell us whether the marble is currently on the ground. Call this function isGrounded. It will need a Boolean output. Call this outIsGrounded. We will use a sphere trace to check if the ground is below the marble. A sphere trace is just like a normal line trace, which is also called a ray trace. The only difference is that it uses a sphere to draw the line instead of a single point. This causes it to check a larger area for contact. This is often a better option when you want to do something like press a button, because it can make it easier for the player to actually hit the button if they have more than a single line used for contact. To do this, we will call a function named sphereTraceByChannel. For the start input of this function, we can pass in the actor location of the marble. For the end input, we will first get the world down vector, which is defined for us in a built-in function. The down vector is a unit vector, so it has a length of 1, so we will multiply this vector by the contact trace distance to give it the correct length. To calculate the final end position, we need to add this vector to the actor location we used for the start position. Now the sphere trace will be fired down until it reaches a distance equal to our contact trace distance. We will use 10 centimeters for the radius of the sphere that we fire, and we can simply return the sphere trace's Boolean value. If the sphere hits anything, we will consider the marble to be grounded. That completes this function. We will now create another very similar function that will check to see if the marble is in contact with any walls. Create a new function called getWallContacts. Give this function one output called outWallContacts with the type integer. What we will do is return +1 if the marble is in contact with a wall on its right side, and -1 if the contacted wall is on its left side. This system could definitely be improved by adding something like an enumeration or a bit set for the wall contacts, because right now if the marble manages to contact a wall on both sides at the same time, then it will actually return 0. This is because it will do +1 for the right wall and -1 for the left wall. But this will work good enough for now, and we'll actually make use of the +1 and -1 in our calculations to make things a little bit simpler. We are going to search for wall contacts using the same method we used for locating the ground. We will do 2 sphere traces. One will go to the right and one will go to the left. Start out the same way by calling sphereTraceByChannel, and then use the actor location as the start. Let's also create a local variable to track the wall contact integer that we will be returning. We will set the value to 0 explicitly in the graph. The variable should default to 0 automatically, but this will ensure the function still works even if someone accidentally gives it a non-zero default value in the details window. Now follow the exact same pattern we used for the ground check. The only difference is that the direction is not universal like it was for the ground, since the ground is always down. Instead, we will need to calculate the correct direction vectors based on what way the marble is currently facing. We will start with the sphere trace to the right. We can use the camera's spring arm to get its right vector. Remember, vectors always start at the origin, so it doesn't really matter that the spring arm is far away from the marble. It will still have the correct right vector, since the spring arm always faces the same direction as the player in the XY plane. Make sure that you multiply the vector that we get by the contact trace distance before using it as the end location. And then change the radius of the sphere to 10 centimeters. To complete this first check, create a branch on the sphere trace's return value. If it is true, we want to increment the wall contacts variable. If it is false, we will do nothing and move on to the next sphere trace. You can now copy the entire sphere trace, because the second one will be almost identical. The only thing that needs to change is the right vector. We are now testing in the left direction, so we want to negate the right vector before doing the multiplication. This will give us the left vector. Now check the return value and decrement the wall contacts variable if the sphere trace hits something to the left. Now we can complete the function by returning the wall contacts variable. It now encodes either a right or left contact with the wall. We now want to create a function to help manage the boost ability. Call this function restoreBoost. This function will be called in a loop whenever the boost ability has been used. It will attempt to refill the boost impulse until it reaches the maximum again. The first thing we will do is get the current value of the boost impulse and add 50 to it. Remember, the boost impulse is something like 3,000, so this will be a small increase each time the function is called. Use the new value to update the boost impulse using a set node. Next, we can check to see if the boost impulse is now greater than or equal to the boost impulse max. If this is true, then the ability is fully restored. In that case, we will clear the timer that will be calling this function on a loop. Use the clear timer by function name node and copy the name of the restore boost function into the function name input. We will start this timer when we handle the boost input action in a moment. We will now finish our work on the marble blueprint by creating a response to each of the marble's input actions. We will start by creating a new function called moveAction. This function will be called in response to the event for the move input action. It will need a single input called inActionValue with the type vector2d. This matches the output of the move input action. The first thing we will do is check to make sure the game stage is play. This is because we don't want the player to be able to directly move the marble when it is being respawned or held in the finished state. Use the game mode reference variable to check the game stage value. If it is true, then we will check the isGrounded function we just defined, because the player will move differently depending on whether they are in contact with the ground or a wall. Let's go back to the isGrounded function quickly and make one change. We want to set it to be a pure function so that it does not require any white execution wires. We can always make a function pure when it does not make any changes to the class. In this case, it is simply calculating a value and returning it. It does not do anything like update one of the marble's variables. We can also set getWallContacts to be pure, because it also does not make any changes to the class, but we cannot set restoreBoost to be pure, because it does update the value of the boost impulse variable. This means that when someone calls this function, we cannot guarantee the marble will be in the same state it was before they called the function. This is what it means for a function to be pure. If you return to the moveAction function, you can see the node has now changed to green and it has no execution input or output. Now create two paths using reroute nodes so we can handle the different movement types. We'll start with the true path, which handles rolling movement along the ground. This calculation here might be a little confusing, so we'll go through some of the details. We are going to apply a torque to the marble. This is a force that causes a rotation. The way we describe a torque is by using a vector that represents the axis we are trying to rotate around. Think about a spinning bicycle tire. In this example, the green vector is the rotation axis. Notice it does not point in the same direction the wheel is going to move. It is actually perpendicular to that direction. The direction of the rotation depends on which direction the torque vector is pointing. If we took the green vector in this picture and made it face the opposite direction on the other side of the wheel, then it would represent a rotation force pushing the wheel in the opposite direction from the red vector. Finally, the strength of the force is determined by the length of the torque vector. So a longer vector would represent a stronger rotational force. This situation with the bicycle wheel is very similar to the one we have with our marble. The main difference is that a marble can rotate in every direction in the XY plane, whereas a bicycle wheel has a fixed axis of rotation. To roll the wheel in a different direction, you have to use the handlebars to rotate the entire wheel, but a marble can rotate left, right, forwards, backwards, diagonal without turning. To handle the rolling movement of the marble, we will allow the player to apply two different torques, and then we will add them together to find the final torque to apply to the marble. We can add together multiple torque vectors to get a final vector to roll the marble in the XY plane. If the player presses A or D, we will apply a torque that would roll the ball left or right. and if they press W or S, we will apply a torque that would roll the ball forwards or backwards. If we add these two torque vectors together, the player will be able to roll the ball in 8 different directions. When we combine this with the ability to rotate the camera, they will be able to roll in any direction in the XY plane. Let's now apply this to the move action. We'll start by getting a reference to the spring arm for the camera. We can use this to get the forward vector and right vector for the marble. The spring arm's forward vector actually points a little bit downwards because it is looking down at the marble. So if you wanted to make this more accurate, you could flatten the forward vector first by dropping the z value. But it doesn't really make that much of a difference in the controls, so we won't bother with that right now. But we do need to negate the forward vector, because otherwise the torque vector for moving right and left would be in the opposite direction from what we expect. To understand why this is, you can look up the right-hand rule for torque if you want to know how to figure out which direction the torque vector should point. We now want to get a reference to the input values that were passed into this function. We can multiply the forward vector by the x input value and the right vector by the y input value. This might still seem backwards if you were thinking of this like normal movement code, but remember that the torque is applied in a direction that is perpendicular to the direction of the force we want to apply to the marble. So if we want movement forwards, we need a torque vector that points to the side. After this, we can add these two vectors together to get the final direction of the torque vector. Then we want to normalize this direction so that it has no effect on the size of the final force vector. Finally, we want to multiply the normalized vector by the ground torque variable we defined, which determines the strength of the rolling force. Now we can get a reference to the mesh and call add torque in radians, passing the final torque vector to the input. Since we are not dealing with the mass of the marble, we can also set excel change to true. That's the entire set of code for the ground movement. Once we finish testing the level, it might be useful to come back here and change around some of these values to get a better sense for how this calculation works. Torque is a very confusing concept the first few times you come across it. Let's now deal with the false branch. At this point, all we know for sure is that the marble is not on the ground. There are basically two possibilities. It is either in the air, in which case the player has no control over it, or it is in contact with a wall, in which case the player is able to do the wall run technique. So the first thing we'll do is call getWallContacts to see if there is currently any contact with a wall. We can check to see if the return value does not equal 0. This means it is either +1 or -1. If this is true, then we want to allow the player to apply a torque to the marble so they can roll along the wall. Start this process by making a new vector. We are going to cheat here to simplify things a little bit. We are going to assume that all walls where the player can do this ability are perfectly vertical. That means we can assume the axis of rotation for all wall runs will always be the z-axis, because when the marble is rolling on a vertical wall, it is basically spinning like a top. So take the wall contact's return value and multiply it by the wall torque variable we defined earlier. This is also a simplification to help make the code easier to write. We are allowing the sign of the wall contact's value to determine which direction we rotate the marble. So if the marble is in contact with a wall on the right, then it will rotate around the positive z-axis because that is represented by a +1. And if the marble is in contact with the wall on the left, it will rotate around the negative z-axis because that is represented by a -1. If you wanted to let the player wall run on walls that were not perfectly vertical, then you'd have to consider the angle of the wall to find the correct axis of rotation. You could not assume the axis was constant because the angle of the walls you were rolling across would not be constant. But for our simplified model, this is all we need to do. We can now call add torque and radians on the mesh again and pass the new vector as the torque input. Finally, set Excel change to true again. The next thing we are going to do is apply some additional forces to the marble when it is performing a wall run. We are going to give the marble a little extra forward movement when it is rolling along a wall, and we're going to apply a small force upwards to counteract the effect of gravity. This will make it so that the ball sticks to the wall a little bit more than it would normally. To begin, we will once again get the forward vector from the spring arm, but in this case we do want to get rid of the z value so that it is not pointing slightly downwards. This is because it would cancel out the force we are applying upwards to keep the marble stuck to the wall. So break the forward vector and then immediately create a new vector with only the xy components. This is equivalent to projecting the vector down onto the xy plane and flattening it. After that, we will normalize the vector because it will now have a length less than 1 since we cleared out the z value. And then we can multiply the output by the wall force variable we defined. Then we can break the vector again to get access to its components and create a new vector that keeps the x and y components and sets the z value to 1000. That is the small upwards force we are adding to somewhat counteract gravity. The marble will still slightly fall while doing a wall run, but not at the same speed it would be in free fall. Now we can get a reference to the mesh and call add force, then use the final vector as the force input. We should also normalize the projected forward vector before multiplying it. Keep in mind, we are no longer applying a torque to roll the ball. This is now a normal force that simply pushes the marble. Finally, set Excel change to true again. We are now entirely done with the move action function. The last thing we need to do is introduce the move input action event into the graph, so return to the event graph. Search for IA move and add the event. We can now call the move action function in response to the triggered output and pass in the action value as an input. We can now define the look action response function. This will be much simpler than the move action. Create a new function called look action with the same in action value input with a vector 2D type. We will now define the exact same response that the main character used for controlling its camera view. Introduce the add controller yaw input and add controller pitch input nodes into the graph. Then break the input vector into its two components. We can use the x component as the value input on the yaw function, and we can use the y component as the value input on the pitch function. There should already be a negate modifier on the y value so that we don't have to flip it here to get the usual inverted controls that most people expect. But if this is missing from your setup, make sure to add it to the look input action. That's the entire look action function. Now we just have to call it from the input action event. So introduce the IA_look event into the event graph and then call look action in response to the triggered output wire, making sure to pass in the action value input. That completes the look action response. Let's now define the jump action function. This function does not need any inputs or outputs. The first thing we'll do is check to see if the game stage is currently equal to play, to make sure the player cannot jump when they are being teleported or held in the end checkpoint. But we also want to AND this boolean with the result from the isGrounded function, because we only want the marble to be able to jump when it is on the ground. You could modify this condition to develop a double jump feature if you kept track of how many times the marble has jumped before it hits the ground again, but for now, we'll just stick with a single jump. We are going to apply a small forward impulse whenever the player jumps to make the jump a little more forgiving for the player. So we will get the forward vector from the spring arm and then multiply it by a constant value. This value will be the strength of the forward impulse during the jump. After this, make a new vector and use the jump impulse variable as the z value. We can then add these two vectors together to get the final vector we are going to use to apply the impulse. We can also turn forward impulse into a variable to make the function more clear and customizable. Now we simply have to return to the event graph and call the jump action function in response to the started output of the IA jump event. That completes the jump action response. We can now define a new function to handle the start input action event. Create a new function called start action. It does not need any inputs or outputs. For this function, we want to check both the game stage and the control stage. We want game stage to equal finished and control stage to equal stasis. This is because the start input should only respond if the player is currently being held in the finished checkpoint. We need to check both stages because the first part of the finished game stage is a tractor phase where the marble is pulled into the position. We do not want the player to be able to teleport back to the start until this tractor phase has finished. If this condition is true, then we are going to set the collision test to true for the spring arm, and then we will call the respawn function on the game mode reference variable. Now we can return to the event graph and introduce the IA start event. We can then call the new start action function in response to the started output wire. We can now write the final input action response function for the boost ability. Call this function boost action. It does not need any inputs or outputs. We will check two conditions to see if the boost ability should be activated. First, we'll check to see if the game stage is equal to play, as we've done with many of the other abilities. Then we'll check to see if the boost impulse is greater than or equal to the boost impulse max. This means the boost is ready to be used. If both of these conditions are true, then we will start by canceling all of the current velocities affecting the marble. We can do this by calling setAllPhysicalLinearVelocity. We will leave the new value input with its default value of the 0 vector. We are now going to calculate the impulse to apply to the marble when the player is using the boost ability. We'll use a very similar process to the one we've used on previous abilities. First, get the spring arms forward vector. Then break it so we can access the individual components. Now create a new vector with only the x and y components to flatten the vector onto the xy plane. Normalize the new projected vector. After that, we'll multiply the vector by the boost impulse variable we defined earlier. And finally, we'll break the vector one more time so that we can add a small upwards impulse when the player uses the boost ability. This is just for improved feel when controlling the marble. When the player boosts, they will still be affected by gravity, so the boost will actually follow a path that is curved downwards. What we are going for is a boost that basically pushes the marble straight forwards for a short time. Adding in a little upwards impulse will partially counteract gravity, so we get a better straight trajectory. Let's also promote this upwards impulse to a variable so that a designer can customize it easier. Now we just need to call add impulse on the mesh to apply this impulse to the marble. After that, let's also be sure to set the boost impulse to 0. This will ensure that the boost will need to recover before the player can use it again. And this is where we're finally going to set the timer that repeats the restore boost function we wrote earlier. Add the set timer by function name node, and then copy the restore boost function name to the input. In this case, we will use 0.03 seconds as the time input. Make sure to also set looping to true. Recall that the restore boost function itself will clear this timer when it determines that the boost impulse is fully recovered. The last thing we need to do is introduce the IA boost event into the event graph, and then call the new boost action function in response to the started output. That completes all of our input action functions. You can take a moment to clean up the graph and then compile and save the blueprint. We are now ready to test all of these features in the level. Make sure that the player start object is in a convenient place to test out your level. Press play and begin testing the move and look actions. You can test the respawn feature by rolling off the edge into the pit. The marble should fade away first, then the camera should return back to the start checkpoint, then the marble should fade back in before being dropped and control returning to the player. You should also be able to use the jump action to get over to the other platforms. You can also test the wall run ability by rolling up to a wall and jumping towards it at a small angle. You should also be able to use the boost ability while performing a wall run or on the ground. So far, it looks like everything is working great. The only thing I noticed that should be fixed is the boost label is a little bit off center. We can open the WBP interface blueprint and simply align it by hand until it looks correct. Now test the level and see if it looks aligned better. The last thing I'm going to do with my build is move these walls because you could probably see there's a little bit of a Z fighting occurring since the walls overlap with the platform next to them. I'm also going to raise up these platforms a bit because the wall run is a bit too difficult to complete every time while testing the level. But other than that, everything looks good now, and this completes the build of the marble rolling game.